Microporous crystalline materials such as zeolites and metal organic frameworks have potential applications for separating a wide variety of mixtures. Essentially, there are two different technologies that can be applied: the pressure swing adsorption technology or permeation across thin layers in membrane constructs. In both cases, the proper description of mixture diffusion inside the pores of microporous materials is of essential importance. In this presentation, I highlight a phenomena that I refer to as slowing down effects. For background information of the material that I will present, you may consult these two publications. Also see this presentation on molecular traffic on my YouTube channel. In order to set the scene for this presentation, let us consider the permeation of a mixture of carbon dioxide and hydrogen across a membrane that consists of a thin layer of MFI zeolite. MFI stands for Mobile 5. It is a crystalline material that consists of a set of intersecting channels, straight channels and zigzag channels, and these are the intersection points. The channel dimensions are approximately 5.5 angstrom in size, and there are 4 intersection sites per unit cell. Let's have a look at the experimental data published by Sandström in 2011 in Journal Membrane Science. They conducted experiments for unary permeation of hydrogen, and the permeance are shown by these open diamonds symbols here. Unary permeance of CO2 shown by the open circles here. So the permeance of hydrogen is significantly higher than the permeance of carbon dioxide. X-axis is the upstream partial pressures. So if you base your expectations on unary permeation data, you would conclude that hydrogen permeates faster than CO2. The situation is quite different in mixtures of CO2 and hydrogen. For permeation of CO2 hydrogen mixtures in which the partial pressures are the same in the upstream compartment, the permeance of CO2 shown by these red circles is about 1.5 orders of magnitude higher than the permeance of hydrogen, shown by these yellow diamonds. So based on mixture permeation, we see that CO2 permeance is significantly higher than hydrogen permeance. And the MFI membrane is CO2 selective for mixture permeation. If you examine the permeances for unary hydrogen, we see there is a lowering in the permeance by about 2 orders of magnitude. The mixture permeance is about 2 orders of magnitude lower than the unary permeance. On the other hand, the permeance of CO2 in the mixture is only slightly lower than the unary permeance of CO2. So we ask the question, why is there a significant reduction in the permeance of hydrogen in the mixture. Let us gain a qualitative understanding how the strongly absorbed CO2 influences the mobility of hydrogen molecules within the intersecting channel structure of MFI zeolite. Let's have a look at the animations. The gray spheres are hydrogen molecules, and we can see that it hops around the channels very fast, but somewhere down the line it has to cross a CO2 molecule, but the CO2 molecule just refuses to vacate its absorption site, and therefore hydrogen cannot bypass the CO2 molecule. In other words, the mobility of hydrogen is reduced due to the presence of strongly absorbed CO2. Here I use the analogy with a checkerboard to explain the slowing down effects that hydrogen experiences in mixtures with CO2 within the intersecting channels of MFI zeolite. Here's the checkerboard where each of these squares represents an absorption site within MFI zeolite. The red circles are CO2 molecules that are strongly absorbed, and therefore each of these red circles vacates or hops to another adjoining site at a frequency that is much lower than the frequency with which hydrogen, the smaller molecule, jumps from one site to an adjacent site and traverses the intersecting channels of MFI. I draw here a contour that the more mobile hydrogen can occupy, but to go beyond that contour, CO2 has to vacate that absorption site. So it is akin to a game of musical chairs. For hydrogen to occupy a chair, that chair has to be first vacated by the tardier, more strongly absorbed CO2. Put another way, the mobility of hydrogen is correlated with the mobility of the tardier partner CO2. And the net result is a slowing down of hydrogen in mixtures containing CO2. The slowing down of the motor cars by the tardier elephants is entirely analogous to the slowing down of hydrogen by the most strongly absorbed tardier CO2 within the intersecting channels of MFI zeolite. For CO2 CH4 mixture diffusion in MFI zeolite, the mobility of methane is severely reduced due to the more tardy CO2 that has a stronger absorption strength. We can have a look at the animation to illustrate that. We can see that the CO2 molecule refuses to budge from the intersection sites, and therefore preventing the methane molecules to travel very far along the channels. Let's examine mixtures of methane and ethane within the MFI channels. The mobility of methane is reduced due to the more strongly adsorbed ethane molecule that vacates the adsorption sites less frequently and therefore slows down the mobility of methane. The same is true for mixtures of propane and methane. Propane molecule is ensconced at the intersection sites and prevents the methane molecule from going past it. So the mobility of methane is reduced by the presence of propane in the mixture. For modeling the slowing down effects in mixture diffusion in microporous crystalline materials, we adopt the Maxwell-Stefan diffusion formulation, which is essentially a frictional formulation. This formulation, the chemical potential gradients, which are the driving forces for diffusion, is considered to be balanced by the friction that component experiences with the wall, with the molecule wall friction, and with the partner species, this is the 1,2 friction. So this is the friction species 1 experiences with the wall, and this is the contribution of the friction it experiences with the partner molecules. Similarly, the driving force, which is the chemical potential gradient of species 2, the driving force for species 2 is balanced by the friction species 2 experiences with species 1, this is the 1,2 friction, plus the friction it experiences with the wall. In the Maxwell-Stefan formulation, we have 3 kinds of diffusivities. D1 and D2 represent the molecule wall interactions, and furthermore, we have a coefficient here, a diffusion coefficient here, D12, which quantifies the correlation effects. So this term represents the or quantifies the extent to which the mobility of species 1 is correlated with that of species 2. Specifically, we will examine mixtures of CO2 and hydrogen, species 1 and species 2, using this formulation. For detailed derivation of the Maxwell-Stefan equations, you can consult this paper. See also my YouTube presentation on diffusion in microporous crystalline materials. Let's examine the magnitudes of these 3 coefficients using MD simulation. This graph presents MD data on the Maxwell-Stefan diffusivities D1, D2, and D12 for mixtures of CO2 and hydrogen in MFI zeolite. The open symbols are the unary diffusivities. This is for hydrogen, which is component 2, D2. This is the one, D2. Unary. This is unary CO2. This is hydrogen in the mixture, D2 in the mixture. This is D1 in the mixture. We see that plotted as a function of the pore occupancy, the Maxwell-Stefan diffusibilities of any component in the mixture is virtually the same as for the unary species. This is a persuasive advantage of the Maxwell-Stefan equations, that you can equate the unary diffusivity to the values in the mixture for D1 and D2, representing molecule wall collisions. In addition, in the mixture, we have the D12 coefficient that can be determined also from MD simulations, and those are shown by these yellow diamonds here. Let's have a look at these values. The D12 coefficient at say at an occupancy of 0.4 is about a factor 10 lower than the value of D2. So D12 is lower than D2. This implies that the 1,2 frictional term, this term, is higher than this term. And for that reason, correlation effects have a greater influence on the diffusion of the more mobile species than on the tardier species, because D1, which is CO2, has a lower value than D12. So the 1,2 frictional term has only a small influence on the fluxes of component 1, which is the tardier species CO2. However, the 1,2 friction has a greater influence on the flux of species 2, which is hydrogen, which is the more mobile species. This is a general conclusion that correlation effects have a greater influence on the fluxes of the more mobile partners in the mixture. Armed with the insights gained on slowing down effects for mixture diffusion in MFI zeolite, we can now attempt to model the Sandstrom experiments shown earlier for permeation of CO2 and hydrogen across an MFI membrane. We use the Maxwell-Stefan equations to model the unary and mixture permeation data. Two different approaches are followed here. Firstly, we attempt to model the permeation data of Sandstrom by ignoring the 1,2 friction altogether. That is shown by the graph on the left-hand side. The dashed lines are the simulations of unary permeances for hydrogen and for CO2, and the continuous solid lines are the Maxwell-Stefan model calculations for mixture diffusion in which 1,2 friction is completely ignored. We see that for CO2, the predictions are not bad at all, but for hydrogen, if we ignore 1,2 friction, the permeance that is predicted is about an order of magnitude higher than the value that is determined experimentally. These are the yellow diamonds here. So the conclusion to be drawn from these simulations is ignore 1,2 friction at your own peril. Let's move on to the right-hand side. We know from molecular dynamics simulations that D12 coefficient is smaller in value than the Maxwell-Stefan diffusivity for hydrogen, D2. Therefore, using the MD data, we are in a position to estimate the value of D12. If we carry out the calculations taking due account of 1,2 friction and introducing the D12 term, we get the mixture permeances shown by the continuous solid lines, and both CO2 and hydrogen are well predicted by the Maxwell-Stefan equations. Therefore, the message to be drawn here is take due account of 1,2 friction, otherwise you will fail to predict mixture permeation across MFI membranes. This is also true in general for, say, membranes consisting of, say, faugesite, magnesium of 74, copper BTC, etc. We now turn our attention to a different class of slowing down effects that is caused by preferential location of certain types of molecules at the channel intersections of MFI zeolite, such as aromatics and branched alkanes. Let's look at benzene. Benzene prefers to locate at the intersections, and it rotates around the intersections and can move along the channels, but its diffusivity along the channels is rather low. The same is true for cyclohexane, shown on the right. Also prefers to locate at the channel intersections, and its motion along the channels is rather restricted. So the preferential location of these aromatics, benzene or cyclic compounds, cyclohexane, at the channel intersections leads to slowing down due to intersection blocking. Let's have a look at a mixture of benzene and methane. Methane has a higher mobility, but the path it follows is restricted due to the fact that the benzene molecule is blocking the intersection sites. This is experimental data on the self-diffusivity of methane with increased loading of benzene. The self-diffusivity of methane is reduced by about 2 orders of magnitude when the loading of benzene corresponds to 2 molecules per unit cell. So the traffic comes to a virtual standstill if more than 2 intersection sites are occupied. the understanding and quantification of such traffic junction effects is of vital importance in the design of fixed bed adsorbers and fixed bed reactors, such as reactors for ethylation of benzene to produce ethylbenzene. Due to legroom considerations, branched alkanes such as isobutane, 2-methylpentane, 2,2-dimethylbutane prefer to locate at the channel intersections. Let's have a look at the animation. On the right-hand side, I show experimental data on the self-diffusibilities of normal butane in a mixture of normal butane and isobutane at a total loading of 4 molecules per unit cell. And we note that the self-diffusibility of normal butane that can locate anywhere along the channels is reduced by about 2 to 3 orders of magnitude when the loading of isobutane is increased in value to more than 2 molecules per unit cell. So the intersections blocking has a severe influence on the mobility of normal butane along the channels. This is another example of how important intersections in MFI zeolite are to the maintenance of free-flowing traffic along the channels. If you block 2 intersections or more, the entire traffic is brought to a standstill. If the intersections are blocked, the entire traffic along this channel and this channel is brought to a complete standstill. For water alcohol mixture diffusion in zeolites and MOFs, there is hydrogen bonding between water and alcohol and between alcohol and alcohol. And this clustering due to hydrogen bonding causes mutual slowing down. The mobility of both partners in the mixture are reduced due to clustering phenomena. Some indication of clustering is also evident for these animations which show clustering of methanol and ethanol mixtures within the cages of Shabasite zeolite. Three types of slowing down effects have been highlighted in this presentation. Slowing down due to correlations in molecular jumps. In this case, the more mobile partner species are slowed down due to correlated jumps with the tardier partners. In the second case, which is specific to MFI zeolite, if the intersections are preferentially occupied by aromatic molecules or cycloalkanes or branch alkanes, This has the effect of slowing down the molecular traffic along the channels. When two or more intersection sites are occupied, the molecular traffic can be brought to a virtual standstill. Finally, we have mutual slowing down due to hydrogen bonding between water alcohol and between alcohol molecules. In this case, the mobility of both partners are reduced due to hydrogen bonding. Also have a look at visualization of molecular traffic on my YouTube channel for other examples.